So this region, what I'm about to do, I did this for ethane, but I got interrupted several times, so it's not a continuous video. And so I decided instead of trying to splice that, I would redo this same thing for benzene and perhaps also again for CO2 so that you can see it twice. Now, the first thing you have to do, and the first thing it's really important for you to realize is the phase diagrams that I am making are representations of the National Institute of Standards and Technology approved equation of state, which is usually a Helmholtz equation of state. It's usually it's a very complex, complicated equation of state. Some usually has somewhere between 50 and 100 something parameters. And it's designed to fit to fairly high accuracy, which means less than 1% error in the pressure, temperature, density range that they provide for you for whatever equation you are looking at. So we are talking a significantly powerful equation of state, and all we are doing is representing that equation of state in graphical form. And I just went through all of that to point out, because as I delete isotherms, add isotherms, delete points, add points, and so forth, I am not deleting and adding data points. So I'm not committing data fraud. I'm deleting and adding points to my graphical representation of a equation that is published and well known. So this NIST Refprop software is calculating the densities through that equation of state using Fortran code. So they're doing a nonlinear solution to a very nonlinear equation to get an accurate density calculation. And that's how they are, that's how the data is being obtained. So when I add points into it to smooth out a line or remove points from it, because I just don't need that many points to show the trend that a particular line is showing, I can do that because the equation of state is continuous for the entire region that I am working in. Now, in my case, the data set that I'm creating is a data set that I'm going to use and compare to computation and to a variety of other things. So I want a data set that has the smallest number of points needed to show the trend lines for each isotherm, but also is smooth and demonstrates the changes in the equation of state. And what that means is I'm going to start out with a particular set that I've selected of pressures and temperatures. And then I'm going to, Gimrel, hush. No. And then I'm going to make adjustments to the spacing as necessary in order to and then I'm going to make adjustments necessary to allow the changes where the most dramatic changes are to be represented. And in general, when you are graphing discretely a function, which we have to do in this case because the function is multivariable, if I am creating a graph using discrete data points on a very complex function, I'm going to increase and decrease the number of data points based on how rapidly the function's changing. So in places of really rapid change, i.e. in places where the derivative, the slope, is changing, I'm going to need more points than in places where the slope or the derivative is non-changing. So you're going to see me do that. Now, the first thing I had to do was make a decision about some starting temperatures and pressures. And again, since in my case, I am planning to continuously use the same starting points for a huge variety of fluids, I needed a very broad variety of starting points. And I needed them to be able to smoothly handle fluids that have critical temperatures of like 40 Kelvin, but also handle fluids with critical temperatures of 400, 500 Kelvin. I needed them to be able to handle things with critical pressures of 10 bar and things with critical pressures of 80 bar with a single data set that I could allow to move and change with each fluid. And the way you do that is with reduced pressures, temperatures, and densities. So reduced pressure is the pressure, whatever pressure you want, your experimental pressure, divided by the critical pressure of the fluid. Reduced temperature is whatever experimental temperature you're measuring, divided by the critical temperature of the fluid. And reduced density is the same pattern, the density of your experimental fluid divided by the critical density of that fluid. So that gives me a way of setting a basic pressure array using reduced pressures. And then that pressure array is something that I can then adapt and modify and change for each fluid that I'm studying, but it gives me a base starting point. So my reduced pressure range, the way I've got it set up, is I need a really, really low pressure to begin with. So I set the reduced pressure of 0.004 as a kind of a zero pressure starting point. And then the next pressure is 0.01, and then 0.02. And then what I'm going to do is I'm going to step between 0.02 and 0.1, step by 0.02. So that means I'll have a 0.02, a 0.04, a 0.06, a 0.08, and then a 0.1. So that's what that notation is going to mean in this notebook. And then because I know that when I'm near the, and then 0.1 to 0.9, I'm going to step by 0.1. Now, at 0.9, I'm getting close to the critical point. And that's that point where I get the most rapid change in density as a function of pressure temperature. So that is a point where the equation of state becomes the most nonlinear. It's the point where everything exhibits the most dramatic changes. So that's the region where I'm going to, again, need to step a little bit smaller. So I'm going to go back to stepping to 1.1. I'm going to step again by 0.02 because that frames the critical region on both sides. And then between 1.1 and 1.4, I'm going to step by 0.1. And then between 1.4 and 3.0, I'm going to step by 0.2. And then from 3.0 to say 10, I'm going to step by 1. Now, that's a starting point. I'm going to make adjustments to this based on two things. I'm going to adjust these pressure ranges based on the maximum pressure of the equation of state, and 2, the maximum pressure of a sample cell. Now, in my case, my sample cell is 450 bar. That's what it's rated to. Well, I have two. I have one that's rated to 130 bar and one that's rated to 450 bar. So the 450 bar is good for temperatures between, I think the lowest it can go is 30 Kelvin to 800 Kelvin. The 130 bar sample cell can go for temperatures 5.5 bar, 5.5 Kelvin to about 400 Kelvin. So these are the conditions of my equipment. And since I'm the one that's doing the modeling, or will be doing the modeling, I'm going to be defining my pressure ranges based on these conditions. So in essence, when I get below 30 Kelvin, I won't bother to calculate up to 450 bar because the sample cell that I've got can't go that cold. And I really think it may even be limited to, I don't think it can even go to 30 Kelvin. I think it may be limited to more like, let's say 100 Kelvin. Because I think it's actually more limited to that. It's a big cell. It's a lot of metal. So we'll say 100 Kelvin to 800 Kelvin. So basically below 100 Kelvin, I'm not going to try to maximize for 450 bar. I'll stay in the 130 bar range. Now, once we have that, we also have, that sets my pressure wave up. Now I also need to set what isotherms am I going to look at. So in a pressure density, a pressure versus density graph, the lines are different temperatures. So that basically means I need to set up a series of temperatures at which I'm going to calculate the density as a function of these pressures. So for molecular gases, now for atomic gases like neon or argon or krypton, where the interactions are small, if I take the triple point temperature, like 83.806, and divide it by the critical temperature, 150.69, I get 0.55. And you might think, well, 0.55 then is good enough for a starting point. But then if I go to molecular gases like benzene, ethane, so if I look at, for instance, at CO2, if I take the triple point temperature of 216.59 and divide it by the critical temperature, 304.13, I get 0.71. as the minimum reduced temperature. And then if I look at, say, benzene, I have a triple point temperature 278.67, a critical temperature of 562.02. That's a 0.50. And then if I look at something like ethane, I have a triple point temperature of 90.368 divided by a critical temperature of 305.32, or 0.30. So the place where gases hit their true freezing point is really, really variable. And that means setting this minimum reduced temperature is in a way that uses reduced variables is incredibly difficult. So I'm going to take the lowest. I'm going to take methane as a starting point, so 0.30. And then I'm going to step by up to 0.90 by 0.05. But I'm going to acknowledge the fact that for a lot of gases, a lot of these isotherms are going to be below the triple point isotherm, and I will have to remove them out of the data set because I just can't calculate them because they're below the triple point isotherm. So they don't exist for the equation of state. Then again, because I'm in the critical region between 0.9, 0.90, and 1.10, I'm going to step by 0.02. And then in the region 1.10 to 1.40, I'm going to step by 0.05. And then between 1.40 and 3, I'm going to step by 0.2. Then between 3 and 10, I will step by 1. And that should be okay. The coldest critical temperature is helium. Helium's critical temperature is 5.19. Which is a reduced density of 57. So after 10, if I need to, I'll go from 10 to say 60, step by 5. But I'm only going to need that last group for really, really cold isotherms just to get to, well, we'll go say 10 to 100, step by 10. How about that? There we go. I'm only going to need to do that last step for really, really cold isotherms. And if I want to be really specific, let's do it this way, 60, step by 5, and then 60 to 100, step by 10. So these last few will be really dependent upon the system in question and how far apart is the critical temperature and critical pressure from room temperature and pressure or from my limits. So again, helium is kind of the lowest on the lowest end. The critical pressure is 2 bar, but it's at 5 Kelvin. So I'm going to be in the 130 bar cell, which again is a 26. So I'll go from 10 to 30, step by 5. That should work. Okay, so how do we now make these pressure waves in terms of an Igor array? So I've already got these in a table. So you basically create a table and you type them in. Now I'm going to check and make sure that since I just made some changes that my array reflects the changes that I just talked you guys through. So 1.0, 1.02 step by to 1 by 0.02, 0.1 to 0.9, yep. And then 2 to 1.1, yep. Then step by 0.1 to 1.4, and then by 0.2 to 3, and then 3 to 10 by 1, and then 10 to 30 by 5. And again, we'll make adjustments on this if I end up over. Okay, so for reduced temperatures, 3 to 9 by 0.05, 0.9 to 1.1 by 0.02, 1.1 to 4 by 0.05, yep, 4 to 3 by 0.2, 3 to 10 by 1, 10 to 60 by 5, and then 70, 80, 90, 100. Hopefully we don't need all of those for most of this. That's a lot of lines on a graph. Okie dokie. So again, we'll thin these out for whatever system we're looking at. This is a starting point, not a final point. So now, how do we go from this to our actual data points for a given gas? So let's start with benzene. So first thing I'm going to do is I'm going to duplicate the pressure to a benzene pressure, and I'm going to duplicate the reduced temperature to a temperature that will be specific for benzene. Now, the pressure for benzene will equal the reduced pressure. So if I go and look, if I want a specific, if I want to take a reduced pressure and convert it to a real experimental pressure for a fluid, I need to take the reduced pressure and multiply it by the critical pressure. Same for temperature, and that's what I'm about to do. So I'm going to take the reduced pressure and I'm going to multiply it by the critical pressure of benzene, which is 49.073. Similarly, I'm going to take the reduced temperature and multiply it by the critical temperature, 562.02, for the benzene experimental temperature, the actual temperature for benzene. And then I'm going to look at both of them. So edit P, T benzene, P benzene. Okie dokie. So here are the two systems. First thing I'm going to ask myself is, what is the triple point vapor density of benzene? Because right now my pressure, my lowest pressure is 0.019. So I need to ask myself, is that above or below the vapor pressure of benzene at the triple point? And the answer is it is below. The pressure at the triple point for benzene is 47 millibars. This is 19 millibars. So that's a good starting point. That's definitely below any pressure that I need that is close to zero. I am good there. And then 49, and I move up in pressure. To go from 19 millibar to 0.5 is probably a little much. So I'm just going to go ahead and insert a point here and do a 0.1. So that's basically 2 orders of magnitude greater than that, but it's a starting point. And then everything else I'm happy with. Okay, now the pressure range for benzene is 5,000 bar, but my sample cell, the best it can do is 450 bar. So these pressures are too high, but 490 is not too high, but I'd rather like a 450 because that's right on the limit of my cell. So I'll just change that to 450 and delete the rest of these. And then 392 is really close to 400 and 350. Yep, we're good there. That's a nice balance. Okay. The minimum temperature for benzene is 278.67. So these we don't need. And 281 is really close to 278, so I'll just make that 278.67. I will leave the rest of these where they are. The highest temperature that benzene can run is 725. So that means all of those are out. And my highest temperature is 725. So now I have taken my steps and I have basically narrowed the temperature isotherms down to what the equation of state can handle. And I've created a pressure wave that also reflects mostly my sample cell. Now what I'm going to do is I'm going to go ahead and clean up both the pressure and the temperature a little bit. So 278.67 is the triple point temperature. I'm going to leave that. The issue though is I've already got on my phase diagram the triple point temperature. It's that. And I already know that the density's kind of, I'm pushing it on the equation of state for that density. That was one of the issues. So what I'm going to do is recognize the fact that that's as good as I'm going to get for the triple point temperature. And I'm actually going to shift this isotherm just a little bit. So I have one at 309, and there's about 30 degrees difference here. So I'll make this about 25 degrees different. So 309 minus 30 would be 279. So if I do 309 minus 25, that'll be 284. And I'm just going to round these values. So 337, 365, because it's my choice what temperatures I use. The only value I am not going to round is the critical temperature, which for some reason is not. Oh, yeah, there it is. Oh, I lost it for a minute. So 450, 478, 506, 517, Now, because of how big the critical region is, in other words, because of just how big this phase diagram is, how broad the temperature range is, I can round to the nearest degree. If I were in a much smaller phase diagram, say for krypton or neon, where my temperatures are all going to be much closer to each other, I might have to round to the nearest 0.1 degrees or 0.01 degrees, depending upon where I'm at. So you have to make a judgment call in terms of your isotherms and how far apart they are. Now, the other thing I know is 562 is the critical isotherm, and the area of biggest change is going to be right here. And right now I have a 10-degree difference in my isotherms here, and that was a 0.02 step, but I think I'm going to need to put at least one isotherm there. Oops, not there. I think I'm going to need to put an isotherm on each side of this because I think the step is too broad. So 562, so that would be 557. And if I do the other side, 562, that would be 568. So that just puts another isotherm in the region where I know that there's going to be the biggest change on each side of that large change. And it may turn out when I graph this that I need more isotherms, but it's a starting point. These are, again, starting points. In terms of this, I'm going to just, again, make this a little bit easier. All I'm doing here is getting a rounding. Don't want to round quite that much for that one. Ah. And again, I want to leave the critical pressure alone and not round that one. But I do want to go ahead and put a point in the region where I know I'm going to be the most sensitive. I can always remove points after I calculate, but I'd rather go ahead and acknowledge that that's a region of high sensitivity and take care of that now. Need to add a point. So all I'm doing here is kind of taking what the relative ones gave me and kind of rounding them to the nearest whole number. With an acknowledgement that that won't hurt. So that gives me a nice near whole number. Now, these pressures, if I was doing a different compound, where I did that, where you'll notice I'm kind of stepping broadly, then narrowly, and then broadly again. Where that occurs is going to be different for every single gas. And that's why initially I start with a reduced pressure, a reduced temperature, scale it up for whatever gas I'm looking at, and then make a decision about what the actual pressure and temperature I'm going to use is going to be for my phase diagram. So this is not something that you can easily write code for, because this truly is a decision-based point. So the reduced temperatures and pressures give me a starting point that then the decision-based ones allow me to continue. Okay, now at this stage, I'm going to take my benzene pressure and temperature. The temperatures are going to be isotherms. Now, when I load this into Refprop, I'm going to need and because I've got pressure first, I'm going to first of all set up my Refprop so that the order matches the order that my table is going to be in Igor. So pressure and then temperature. Now, if I want to do this the most rapid way, I'm going to be using calculate specified state points. If I want to do this the most rapid way possible, then I'm going to need a temperature array that's the exact same length, the exact same number of points as the pressure array. So I'm going to duplicate the pressure array into a temporary temperature array. And I'm just going to call it temp because it is temporary and it's not going to be something that I keep. And I'm going to add that to this table using append to table. And you'll see it's just a duplicate of pressure. And now I'm going to set that temperature wave by typing temp equals to the first of my temperatures in my isotherms. So that would be 284. So now you see I have pressure, I have temperature, I have the same number of points in each of these. So if I copy these two and paste them into here, I get a series of pressure temperatures. And you'll see, sorry, the headphones hurting my ears. And you will see that at some point it says I've got a density above the density limit of the equation of state, which is 11.45. Do I want it to calculate? You can just hit yes all. You'll see it doesn't calculate these points, and that's fine. So it calculated as far as it could calculate, and now I copy those. Now I want this to go into the real gas region, so I'm going to create a new table and paste all three of those waves into the new table. I'm going to rename them. This is temperature 284 Kelvin. Oops, no, pressure 284 Kelvin, temperature 284 Kelvin, and density 284 Kelvin. Now the final thing you'll notice is I have a real big density change between 0.02 and 0.1. And that's because I'm at a temperature below the critical temperature. And that means that I am at a place where I'm going to hit that 2-phase region. That means I'm going to need to add a point, 2 points, where I can acknowledge the vapor pressure and the vapor and liquid density at that vapor pressure when both phases are in equilibrium with each other. So I will calculate saturation points. I want to calculate that at 284. So the pressure, shift that, I can see. So the pressure is 0.063492, 0.063492, and the density of the vapor is that, and the density of the liquid is that. And now when I append these to this graph, when I append to graph the pressure, 284 K, versus the density, you'll see I get a nice straight line with a slight angle to it, and then I get a little bit of a vapor pressure line. So we're doing good there. When I get higher up, I'll show you why we have to make sure that we actually put the phase transition point in. Because what happens is if you don't get, the tie line is not straight. So it's really important to take the time to do that. Okay, so now make sure I have this table where I can access it. It's always so much fun getting everything you need on the screen, even a wide screen. There we go. Okay, so now I have one of two options at this point, because technically this is in one directory in terms of data browser. So I'm in the real directory, but the temperature thing that I need to change is in the benzene directory. So now what I need to type is root : benzene : temp is equal to 309. And you'll see that changes that. And copy these two. Now, since I know I'm going to need that, and I've got this table open, I'm going to go ahead and use that, put that in. Let's slide this table down here where I can see it. And I'm going to paste. Now at 309, it calculated all of the densities except the last one. So I will copy these, paste these, rename. So pressure 309 Kelvin, temperature 309 Kelvin, density 309 Kelvin. So that takes care of that. I will find where my phase transition is. It's right there. Add 2 points. I will look at my saturation table in NIST and type the vapor pressure. And then the density of the vapor and the density of the liquid. And you'll look at that and you go, wait, the density of the liquid didn't change that much. And no, it's not uber sensitive. These lines are pretty straight in the region right now. They're going to get more curved as I move up this line. And I get to less cold temperatures. And then I'm going to append the the pressure, 309 Kelvin versus the density, 309 Kelvin. And now you can see I'm now at almost 400. Now, for right now, so that I can see the region I'm most interested in, the more sensitive region, I'm going to keep zoomed up at 100, where I can keep an eye on this region. Then my next temperature is 337. I just copied from the history and then changed the temperature. And then same thing here. I'm going to copy this, put my temperature there, and paste into here, 337, and check and see if this time I didn't hit the maximum density, so it didn't bottom out. So I have all the way to 450. Copy that, paste, change the names. This is 337K, temperature 337K, okay. Look for the place where my density changes, because that's the, if you're curious and you're asking yourself, but you know, it's such a dramatic change. Yes, it is singular. It is, if from a function perspective, the density change at that vapor pressure line, that change is a discontinuity in the function defined by the vapor pressure. And it's exceptionally hard to calculate that. And in that's part of the reason why it has to switch equations when you get to right at the vapor pressure. So when you're calculating this, when you are coding it, you literally code where you check the temperature to see if you're below the critical temperature. When you are, you then calculate, you use the vapor pressure equation to calculate the vapor pressure. Then you check to see, is the pressure that I've been given less than the vapor pressure or greater than the vapor pressure? And based on that answer, you start looking for a solution to the density between the density at the liquid and higher, or the density of the vapor and lower. So it is truly a discontinuity in the equation of state. And that's in fact why we have to do it this way, why we have to input it in as a discontinuity. 2 points. So in essence, the vapor pressure, that phase change, is a place where your function is not single valued. It's a double valued function. At the triple point, it's a triple valued function. So that's why you have to do something like this, is you are technically plotting a double valued function at a single point in this complex diagram. Okay, so after 337, the next point is, oh, gotta pin that to graph. Okay, so the next point is You can copy and paste. I'm not bothering to copy and paste just because I type numbers really fast after experience. You can copy and paste the values if you choose. That's and I'm just going to keep working my way up, one step at a time. Not uber tedious, it's just, but you can see by using the reduced density, I've at least got these isotherms um, consistently spaced so that they look nice on a graph and nobody's going to question why they are the way they are. You can also see that where I have to insert a point is shifting for as I move up to higher temperature. And that's because that vapor pressure is a function of temperature. And at each temperature, that vapor pressure gets higher. And as does the vapor density, and the liquid density gets lower. Doesn't make it any less linear though. Now here, I need to actually take a little look. So what I need to look at here is the spacing between these 3 points even and not super large? So I've got a 0.03 spacing here, 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 and here. So that's going to be pretty smooth. And is the spacing here still okay? It's like 0.1015, 0.015. So yes, and yes. Because as this shifts down, we're going to get into the region where we have maybe more points or less points, and we may need to add points or get rid of points uh, just to keep the line smooth on both sides. Because remember, as I said before, our initial starting point is a guide. It's not a tell-all. So we may have to make adjustments as we continue on. And those adjustments are to smooth out both sides of this line, not just one side or the other. Now at the end of this, the other adjustment that we will make has to do with the total number of points in this curve as a whole. And that's an adjustment that as students, you wouldn't inherently make. And that's because it doesn't really matter if you have too many points in the line, it still represents the trend. But if you're going to be spending time calculating points and comparing calculated values to actual values, and when you're doing that, when you're doing theory and you're comparing it, you will be comparing back to these data points because this equation of state for benzene is accurate to 0.1%. So it's in essence the experimental data, or it replicates the experimental data precisely. And given that, if you're going to calculate and compare, you're going to compare back to this equation of state. And calculating stuff takes time, so you're going to want to reduce the number of points you're calculating. And that means that you're going to go back through this data set, which is something we're going to do at the end of this and just shortly. And you're going to remove points out of these arrays to reduce the total number of points that you would need to, quote, calculate. And again, that's something that as a student you wouldn't inherently do, but as a person who's going to be using these data sets for calculation, it is something I'm definitely going to be doing. So let me continue. Let's see how much time I've been on this. So it's an hour long. So even though I don't tend to like to skip points, I'm going to move on up to plot at 422. I'm going to step us on up to a temperature closer to the critical temperature, say 540, but still below the critical temperature. I'm going to do that so that you can see first of all how far the density change is shifted. So now the density change is all the way down here. So I am at, oops, I put the points in the wrong spot. I need to delete those points and add them to there. Try that again. So 37.207, 540, 540, and 1.5408, 6.5156. Okay, so now when I add that one, you change the name here. P540K, T540K, T540K. Now I'm going to go back and I'm going to add all of the rest of the isotherms between 540 and 422. What I predominantly want to show you here is while this isotherm is very smooth, if I look over here, it is not very smooth. And the reason for that is if I look at lines and markers instead of just a line, you can see my area of where I have a lot of points is not quite in the right spot for this. So you can see it's a little bit rough here, and I might want a couple more points in this region. So I'm going to go ahead and calculate those points. And I can just use the table I'm copied into because I'm going to be making up the points. So the points where I'm going to be making them up are on the pressure side. I want one more point between here and here. So that would be this. And it's 35 and 37, so 36 is a good point. I'll just come over here and tell it I want to calculate 36 bar at a temperature of 540. And it's going to give me the density. And now you see I have a smooth point there. And I'm going to put another one right here. And again, I'm going to just evenly space it there. Now, if I look at that, you'll see that while it's evenly spaced in pressure, it's actually not evenly spaced in density, and it still looks a little. So I think I'd rather it evenly spaced in density at that point. So what I'm going to do is I'm just going to take my density and calculate the density that I want, which is 1.14. And I'm going to come back over here, and instead of having it calculate the pressure, I'm going to ask it to calculate the pressure for the density that I want. Now you see I have a much more evenly spaced density within the X variable instead of the Y variable. And that gives me a nice looking line, and the rest of the line's fine. So that takes care of that size. And then on this side, you can see I have way too many points in the region where it doesn't change. So what I'll do there is that's on this side. So here's where the change is. And I go from 40. 40 looks okay. I probably do not, because this one's at 40. 45, I probably could just deal with 45. So I will delete that point. Could probably do just fine all the way to 50. So I will delete all of those points. Oops. Oh, shit. And that was a mistake because I didn't actually delete the density. When you make a mistake like that, don't panic. You can't undo it, but you see it put the points I deleted in the history. So I need to delete those same points out of density. So I copy the command to the active line and convert pressure temperature to density, and you see that fixed the issue. That gives me an evenly spaced there, and I probably don't need these points. And now you see I have an evenly spaced set of points. So this is where most of the curvature is, and I fix that. Then I come over, and I have a slightly curved function there, and I've handled that. So now that's all nice and smooth. Now, in the end, since we're doing this, if I go ahead and look at all of these, this function is curved, and I'm handling the curve, and then it kind of becomes not curved here. And I've got just a few points there. So if I'm asking myself, which points do I need, which points do I not need, even here, these are probably fine. So say 150, but I can probably get rid of the 150 to 100 and still be able to see the curvature. In other words, still get a nice smooth line. Now from 100 on, I've got enough curve that I can't do that, at least not for this temperature density. So let's do that again for the next one. So I'm going to put this back lines between points so that you can watch me do that one more time. So see, I have a nice smooth line in, nice smooth line out. Hopefully I won't mess it up this second time. So let's do the next 551. Oops. Okay. Make sure I copy only what I need. So there's my 551. Same thing as before. I find where I have the discontinuity in density. Put my discontinuous point in. And then do the same thing as before, where I ask myself, well, let me go ahead and get these on. So this is pressure, 551 Kelvin, temperature 551 Kelvin, density 551 Kelvin. Same thing here. I need to pin to graph. Pressure 551 Kelvin versus density 551 Kelvin. And then same thing as before, I'm going to want to smooth out each side. And it can be helpful to see your markers. And you can see the place of too many points is getting closer to where I actually want it. So the region I want to look at is just this region. And you can see it's very discontinuous here, and it looks fine on this side. But I can certainly get rid of a few points. So I'm going to go ahead on this side and .44 is fine. Maybe keep every 2. So 44, 46, 48, 50, 52, 54, 'Now I could either make that 56 and then go straight to 60, 65, which would evenly space it, or I can just have one slightly bigger space. I think I will make this 56 and come over here and just calculate 56 for 551, which would be 6.5375. So that gives me evenly spaced there. And if I want to check it, you can see how smooth and evenly spaced I am. And I'm pleased with that. I'll check the 400 in a minute. So now if I look at my, say, 20 to 50 range on the low density side, I clearly need to add a couple of points in this region. So I've got too much space here. And you can see this is about 1.6 on the density. That's a 2, so maybe a 1.8 density would be, smooth that out a little. So I'll come to this and 551, 1.8. So that would give me 41.625. And then in this region, I have 1.6 and 1.2, so the same thing. So that's 1.2, that's roughly 1.6, but it's perfect. So this would be, say, 1.38. Or 37.791. So now, again, I've smoothed this transition out. And now that I'm out of the region of change, I'll just let it go evenly spaced yet again in the way that I had it. Now in the gas region, again, reducing the total number of points there. Don't need all these points down here. Maintaining the order of magnitude. So this and this are an order of magnitude difference. That's an order of magnitude different, but this point is not really. I mean, it's kind of nice. It's 1 bar, but it's not that necessary. So that gets rid of a point there. That's about 0.04. So if I get rid of this point, that evenly spaces us there. And then here I have 0.09 to 0.2. If I get rid of this point, that's a pretty big jump because here I go from 0.2 to point. So I have about 0.15 difference here. So if I shoot that difference, so 0.23 minus 0.15 is 0.08. So if I aim for this to be, say, I delete that. You have too big a jump there. So I kind of want the difference between those 2 points. So 0.23 plus 0.09 div 2, so about 0.16. And now I need the pressure for that. So 551, 0.16, 6.9375. And now that gives me a smooth transition in the low density, and then a smooth line up and into the curvature at near the vapor pressure. So that kind of keeps it smooth all the way through. And that's what we're aiming for, is a kind of a smooth line all the way through with the bare minimum of points necessary to do that. And then on this one, the same type thing. So if I look at these points, I've got a nice smooth transition. I've got too many points there. So to 50, I'm good. which is right here. I am not sure I need that point. Uh, 150 does not look like I need these. Maybe. So what I'm going to do, I need some points there. I just don't need as many as I had. So what I'm going to do is I'm going to put back some points. But instead of stepping by 10, I'm going to step by 20. So that smooths that back out again and steps by 20. And then transitions us into 10s, 90, 80, 70, 60. And I do think I'm going to put 58 back there. I got rid of it, but no, I don't need that one. So what I'm looking at is how even, you see it's kind of evenly spaced density wise here. It gets a little bit tight there. So let me look. So 5.9, that's 0.1, 0.1. So that's roughly 1.5. Don't think I really need that one. There we go, 0.15. Don't really need that one. 0.15. I add 0.15 to this, that's roughly 30, so 6.45, it would be 6.45, 50, 60. So don't really need that one. So that's 0.64, and now I'm stepping 20, and then a 0.5 again, and then 0.5. So I'm okay with that, actually. 0.5, 0.5. That one, 0.5, 0.5. Yep, okay. So that smooths us on out, reduces the number of points overall, gives us a nice smooth line. So again, this is something you do by eye, but you have to start somewhere. And of course, the somewhere that we normally start with is a base that we can then make adjustments to. So at this stage, I'm going to stop this video because it's an hour and 30 minutes long. This shows you how to go about doing the region below the critical isotherm where we have that break. And then once I finish it for benzene, I'll come back and show you the critical isotherm and then the region above the critical isotherm.